So I'm talking about polynomial preconditioning, and it was supposed to be on both linear equations and eigenvalues. And 15 minutes, I won't have time to even mention eigenvalues at all, but we'll get to the linear equations. And this is work with Jennifer Lowe and Mark Embry. Okay, so in this talk, polynomial preconditioning really has amazing potential, and so I want I'll just have a couple examples that show that, but I think they really make that point. And we also want to mention reducing dot products and other vector operations, which is important these days. I want to show some pictures of animals. Why not? We might even see a slow loris. That may be the highlight of the talk. And then we're going to talk about stability of polynomial preconditioning, and that there's a lot more work to do. Okay. So I've never been to southern France. I'd like to get there. My only time in France was my wife and I took all our kids 11 years ago, all 4 kids, and we had 24 hours to tour Paris, and we saw a lot. It was amazing what you could see riding the subway. It was a lot of fun. So what about polynomial preconditioning? There's been so much work done on it, and it goes back a long time. There's still some work being done on it, but really, I would say that the main thing to realize about polynomial preconditioning is that it hasn't been used very much. It's been talked about a lot, but it hasn't been used very much. I mean, some people are using it now, but not a lot. And I think part of the reason, this is speculation, but I think part of the reason is in a lot of the papers, it's fairly complicated to implement it, especially when you have an unsymmetric matrix. And due to that complication, and I don't know what else. I don't know what the other reasons are. Somehow it never really caught on, and yet it can be an amazing method. I mean, I went to talks back in the 80s and 90s and thought, oh, that's interesting, but I never really thought to try it. And then I needed it for this application. I thought, wow, this really works good. And it just led me into this, just needing it for a very specific thing. And just the way it worked got me convinced. Okay, so a lot of people think it's boring. Some of the referees of our papers have thought polynomial preconditioning is boring. Not very interesting. Kind of an old method that didn't pan out. So I hope to convince you otherwise. Some people think it's like Texas weather in the summer. You know, every day's pretty much the same. I live in Texas, so I can attest to that. I was trying to think what would be boring in France, and I couldn't come up with anything. I thought another cafe, but I'm not saying that's boring. I just couldn't think of what would be boring in France. But I want to convince you, don't quit on polynomial preconditioning. It's kind of like this little bear that the Polish army adopted in Syria during World War II. Corporal Wojtek is the bear's name. And they weren't allowed to take him. When they were moved from Syria to Italy, they weren't allowed to take him. So they fully inducted him as a soldier in the Polish army, and then they were allowed to take him. And he served so well, he was later promoted to he started off as private, and he's later promoted to Corporal Wojtek. Okay, so let's not quit on polynomial preconditioning. So I hope this example will convince you there's potential for it. A biharmonic matrix. And with no polynomial preconditioning, it takes almost 15 hours. With polynomial preconditioning, you can run it in seconds. That's how much the polynomial preconditioning helps. And I forget what else I was supposed to say here. Let's go to the next slide. It's as exciting as swimming with pigs in the Bahamas or sharks with the Bahamas. This is an excuse to show my vacation pictures. But it's not from 2020. No, it's from 2019, those pictures. And so how do we implement this? It has to be simple enough that people want to use it. And the way we polynomial precondition Gmrs is to use, believe it or not, the Gmrs polynomial. So first we have a Gmrs to develop the polynomial out to whatever degree we want the polynomial to be. And then we apply that polynomial to a restarted GMRS, okay? And we implement it using the roots of the Gmrs polynomial, which are the harmonic Ritz values. And why does it work so good? Well, I like to think of it in terms of chihuahuas. If you Scott is the bear. And here are two of our bears that live on campus at Baylor University. And I was just thinking, while making out this talk, they're even more powerful than German Shepherds. I would want a bear with me in the dark alley. And that brings us back to Corporal Wojtek. And you can see he grew up during the war. And in Italy, he saw soldiers carrying ammunition boxes. And the story is he would carry a box that took 4 men to carry it. He would carry it by himself. And he served so well. I already told you this. He got promoted to corporal. So that's the power of polynomial preconditioning in my mind. That's how I look at it. The power of having a bear with you to help. Okay, so here's an example of a Gmrs polynomial. We have up here on top, the green one is degree 5. The red one is degree 25. And you can see most of the eigenvalues, they map to near 1. This is just the basic idea of polynomial preconditioning. And so it makes the spectrum a lot easier when most of the eigenvalues are near 1. Now, some aren't. You still have some small ones, but you have less of them that are spread out from 1, that are near the origin. They're spread from origin. Depends on the slope of the polynomial at the origin, how much they're spread out. So that's the basic idea. Let's go on. And I want to talk about dot products now because no one seems to like dot products. I mean, I have nothing against them, but you go to talks and people really don't like dot products. They're like having a cockroach as a pet, which no one seems to want. We had one for 3 years. It was a Madagascar hissing cockroach, which my daughter brought home. It was like 20 years ago at least, and lived a long time. And the Sloloris, there it is. No one wants that as a pet because it's the only poisonous primate. But if you don't want dot products, polynomial preconditioning can really help you with those. Let's go back to our example we had a second ago. This takes a little while to skip through, doesn't it? Okay. Whoops, I forgot how far up it was. Okay, so for this biharmonic matrix, look how much the dot products are reduced by a factor of over 100,000. And why is that? Because you have so much more power in each iteration, you have less iterations, and so a lot less orthogonalization, a lot less dot products. I better start moving this while I'm talking because it takes a while to get down. I should have had that slide closer. Okay, so we reduced dot products by a factor of 100,000, an amazing thing. It's not always that good. I should talk about that. How good can it be? For a really difficult problem, we did some analysis using Chebyshev estimates. So this is just an estimate, but it's amazing how much polynomial preconditioning can improve things. Here's kind of the bottom line in gold down here, the next to last line. If you have a degree D polynomial, you can reduce the matrix vector products by approximately a factor of D. So if you have a degree 100 polynomial, you reduce matrix vector products by a factor of 100. Again, that's not always true. That is only for a very difficult problem. It's kind of an asymptotic thing. For the most difficult problem, you can reduce that much, and dot products even more by a factor of D squared. But what if you don't have a difficult problem? Is polynomial preconditioning worthwhile for you? Maybe, maybe not. If you have one of these, I've seen talks where people have their preconditioners so good, they have 4 Gmrs iterations. You don't need polynomial preconditioning. Just don't even fool with it, okay? Here's an example of an easier problem. It's the same tough matrix, the biharmonic, but we use ILU0 preconditioning after a shift, and so it makes the problem a lot easier. And here, polynomial preconditioning still helps, but not as much. If you had a really powerful preconditioner, maybe you wouldn't need polynomial preconditioning at all. But with this preconditioner, we reduce from minutes to seconds. So it's still useful for this case. So it depends on how hard your problem is. Okay. See how I'm doing for time. So here's a baby QCD problem, quantum chromodynamics. It's just a little one. Usually they're millions by millions. And you can see it helps here, reduces from 36 minutes to 53 seconds, and with just a degree 50 polynomial. What real reason I put in this example is to show you what the polynomial looks like. Now, the spectrum is complex for a QCD matrix, and so we can't really graph the polynomial. We need 4 dimensions, but here's a graph of the absolute value of the polynomial. And the spectrum, I should have slashed it up, but it's basically a circle. No, not a circle, but contained in a circle. And so you can see how that polynomial, this is just degree 10 polynomial, it flattens out in this circular area where all the eigenvalues are. It's kind of amazing how well it looks, how well it works, and how well that polynomial looks. And it comes down to 0 at 0 like it's supposed to. Okay, let's go on. We have the real part of the polynomial. We can plot that, and the imaginary part. I won't dwell on those, but again, they have to flatten out. Now I want to talk about stability. Here's an example of a matrix with regular preconditioning, and you can see that with degree 6 polynomial, it converges fine, but with these higher degrees, it does bad, even terrible. So what's the problem? For this matrix, it has a well-separated eigenvalue, an outlier, and as a result of this, the polynomial, just look at this green polynomial, ignore the other ones. With this green dash polynomial, it has very steep slope at that outstanding eigenvalues. It doesn't look that steep till you look at the scale up here in the corner, 10 to the 17th. So it is very steep. Because it's so steep, it makes it dealing with that polynomial an ill-conditioned problem. So what should we do? How do we get rid of those steep slopes? Not everyone can be in Texas where there are no steep slopes. So we're going to change the polynomial. We're going to make those outstanding roots double or triple. I'm running short on time, I think. So I won't, well, I didn't want to go through this anyway, so it's a good excuse. But we do have an automatic procedure for how to assign the double roots, triple roots, whatever you need. And it works well for that example. It makes those methods that did not converge before, now they all converge to 10 to the minus 10th. And you can see the red polynomial has a double root and the blue polynomial has a triple root at that outstanding eigenvalues, and it makes them much better behaved as far as steep slopes. Okay. Let's see. I have another example. I think I won't do it because I'm supposed to be wrapping up in time around now. Another one with outstanding eigenvalues. Let's skip that one. Oh, well, I can show you the results. Instead of having stability problems where with degree 35 polynomial, it doesn't converge. Now, even with degree polynomial up to 75, it converges to good accuracy. But you have to add 61 extra roots to it. It's kind of amazing. I'm not saying you always want to add that many. Usually you don't need to. It depends on how many outstanding roots you have. But I just thought it's amazing. We're adding 61 extra roots and it still works. Too many extra roots, it won't work. And I think we need to work on the ordering of the roots of the polynomial. With 115 added roots, it didn't work so good. Okay, I'm going to skip that. I think we're headed for the conclusion. We did comparisons to BiCG stab, to FGMRes. Okay, so anyway, the conclusion is I hope people will try polynomial preconditioning. It has a lot of potential, especially for new computers coming out these days, where communication, dot products and stuff like that is a big deal. I think it can help in maybe a simpler way than a lot of the ideas that are being looked at for reducing communication. A lot more to do with indefinite linear equations, non-restarted methods, least squares problems, etc. And okay, I think that wraps it up.
Okay, thank you very much, Ron. That's for a very nice talk again, and thank you again for all of the animals, including the poisonous.
Thank you.
So we have some questions here. Jeffrey Cornelius asks, how would you choose an optimal degree for the polynomial?
Yes, a referee has asked us that too. Okay. No, I'm not going to even try to do that. We usually try 50. Yeah, no, try 50. Yeah, 50. But does that mean it's optimal? No, it really depends on the problem. And in general, if the problem's tougher, you're likely going to need a higher degree polynomial. Whereas if you have an easier problem, suppose you have a really easy problem and you're not even sure if polynomial preconditioning will help. Try degree 5 or something like that. And if you see it's not improving the matrix vector products, then check, is it improving the dot products enough to make up for that? Maybe it will, maybe it won't. Depends on how easy the problem is. I mean, that's a good question. We don't have a great answer for that, though. We haven't tried to automate that.
So there's another question here from Catherine Lund. She asks, or she says, this is a weird musing. Do you think that polynomial preconditioning might be equivalent to rational Krylov for linear systems, where you use an iterative method for inner solves?
Well, I haven't thought of them as being in any way similar because, well, I mean, both are improving things, trying to improve the spectrum, map the spectrum a different way. But of course, in one, you're allowed to factor the matrix. Yeah, I'm sure there's some relationship between them because people who start off with trying to work on a polynomial may end up doing the rational. You know, they realize we need even more. We need even more power. I guess that's kind of, these would kind of be steps in trying to improve things.
Anyway, does that, okay, so yeah, I think. So there's another question here from Wim van Roos, who asks, have you looked at communication avoiding SPMV kernels, sparse matrix kernels, to implement the polynomial?
No, I personally have mostly avoided communication avoiding stuff. I'm fine with dot products even. You know, they don't bother me. I just want to throw it out there that some things can be done. No, I've done nothing whatsoever on that. Now, Jennifer Lowe, one of the co-authors on this, she's getting into communication avoiding stuff. I don't think she's done what that question was. I won't even try to repeat it, but she's looking at some things. So eventually, maybe.
Okay.
She's probably listening right now. She's giving a talk later on.
Okay.
Yeah.
And there's a question from Kumar, who says, how do you combine polynomial preconditioning with ILU0 in GMRes? Do you use GMRes or do you use FGMRes to combine the two preconditioners, ILU and?
Oh no, yeah, you don't need to go to FGMRes. The polynomial preconditioner can be applied to any preconditioned GMRes. It's easy to do. I can't show. I don't have it on my slides, so I can't show you. But it's trivial to have a preconditioner and then add in the polynomial preconditioning.
Sounds like Kumar should meet up with Ron in that next gather session and carry on asking those things. Can I just ask one question myself? And that is that
sure.
You spent some time. You talked about some difficult problems at the end, but you talked about biharmonic initially. So the biharmonic problem is self-adjoint, and yet you still use GMRes. Is it always true you have to use GMRes for symmetric problems?
No, you can polynomial preconditioning conjugate gradient. You don't get as much benefit, but you can still reduce the vector operations. And that biharmonic, I didn't put it up. It actually was non-symmetric. I added in some other terms to it. Okay. But of course, if it was purely, you're right, of course, if it was purely biharmonic, that would be symmetric. No, you don't have to go to GMRes. It can be more efficient on conjugate gradient or MinRes. If you were doing eigenvalues, which I said I wasn't going to get into, you could do, instead of Arnoldi, restart Arnoldi, you could do a restarted Lanczos, thick restart Lanczos or something like that. It can be applied to all of those.
Okay, well, thank you very much, Ron. Let me give the metaphorical applause again for a nice talk.